Hello everyone, this is Ben from Chicago Bright, and today we're going over another problem in the 1956 Tokyo University entrance exam. This is the second problem in the exam for STEM majors, and I want to first off start by just looking at the problem quickly, which is it says fill in the blank with the correct number. The following system of linear equations has infinitely many solutions if k is equal to blank and L is equal to blank. So when we look at this system of equations, it's something that a lot of students in high school in the United States don't really see because usually when we talk about system of equations, we don't really talk about 3D lines or three variable linear equations. Usually we talk about two variable systems of linear equations. So I actually don't want to worry too much about solving this for now. I always want to try to start by doing something a bit easier, something that is more familiar with everyone. So let's think about this from instead of the context of like a three-dimensional line or a three-variable line to just something we're more familiar with, which is like a two-dimensional line. And in our case, we're also gonna make a two-variable. So I'm gonna say like, for example, x plus 3y is equal to 0, and then 2x plus y is equal to 5. Okay, so whenever we see these type of system of equations, I think a lot of students are very quick to say, oh, these are really easy to solve. All I need to do is either substitution or elimination. And yes, both of those will get you an answer, but we have to be very careful with why we do those things. A lot of students are very used to seeing the same problem. They see the same scenario, they see the system of equations, and say, okay, like I already know how to solve this. My teacher has shown me the method of either substitution or elimination. I want to be very careful with this type of mindset because it's really important to understand why that even makes sense as a way of understanding these or how we can get those solutions. So let's start with just one of these equations. So 5x plus 3y is equal to 0. When we look at this equation, there's some things I always like to ask. The first is, why is it that I can't just immediately assign a value to x and y? Why is it that that's just left as x and y, for example? The reason why this is important is, let's think about an equation with only one variable. If I gave you an equation like this is immediately solvable. You just told me x is equal to 0. And there's no other answer that would actually work here. I can't choose any other number for x that would be valid in this situation. Now on the other hand, if I let's say said x is equal to 0 for this line, or this equation, what happens? Well, my y in this case would also have to be 0. On the other hand, let's say x is equal to, I don't know, um, negative, negative 3. Then y would have to equal 5. If we look, the problem here is we technically have infinite choices involved with x and y. Now, when I say infinite choices, I don't simply mean that I can choose whatever x and y I want. There's still sort of a rule involved with this equation, which is that this has to be that 5x plus 3y has to equal 0. Or I can manipulate this equation a little more if I want to get a more direct relationship. When we think about this, I always think it's important to think about this in context of a graph or an equation that we can actually look at. So, okay. I'm not going to be too accurate with the drawings, but in our case here, let's think about what we can do with this form. So I know a lot of students like to immediately move this to a form that they might either like, or maybe they're more used to this form anyways, where they might try to change this into y-intercept form, where it looks like y equals mx plus b, or something like that. But I want to always tell people that it's worth a shot to better understand why other forms are used and why we could take advantage of it in this case. Now for this one, it kind of tells us exactly where our zeros are. So for example, if we set y is equal to 0, we can get what x is immediately, which is 0. And if y, it's also 0. So in this case, we have 0, 0. Now it's a little more annoying because usually these type of equations, the goal would be that we get both a point in the y-intercept and the x-intercept, and then we can easily draw a line. Because any line, if we have 2 points, is easily writable. But this is, we can kind of imagine immediately the slope is always going to be, if we have this form of ax plus by is equal to c, it's always going to be negative a over b. So in this case, it's negative 5 over 3. So we can just imagine kind of slightly steep slope. So let's say something that looks kind of like this. As I said, the drawings won't be too accurate today, but we can kind of work with that. The next one we'll look at is 2x plus y. Now let's think about exactly what's happening, that when we have two lines, that somehow we can get a solution, that we can get one x and one y value that is valid for this equation, or this system of equations. Well, when we look at this, we're basically saying, let's draw another line. So in this case, y would be somewhere like 5, and this is like negative 5 over 2, so 2.5. Let's just say it's like somewhere like this. And we kind of draw this line out. And for this case, let's draw it slightly cleaner. That's good enough. And at some point, these two lines meet together. So like here, for example. What we're saying when we talk about system of equations is we're saying, well, can you tell me a point that exists where both of these lines share that same value? In this case, it would be this value. Now, there's all types of different scenarios where we can get more than 1 points. What if instead of just line equations, we had a parabola, for example, or a nonlinear graph? Then obviously we have more than one solution. But even within the context of lines, there are scenarios where we don't only just get one solution. What happens if both lines represent a very similar thing, or the same thing? So in this case, right now we have 5x plus 3y equals 0. What if the bottom one was just a double of it, so 10x plus 6y equals 0? The question is, do I get more information that can cause me to figure out if there is some intersection involved with this? If I were to double all of this, is that realistically actually any new information that's provided to me by this new equation? And the answer is no, because if I multiply or divide 2 by both sides here, I get the same equation. So realistically, I'm actually not getting any new information or a new line with this equation. So they would just be on top of each other, and in other words, I would still get infinite solutions as if I only had one line. On the other hand, what happens if both lines are parallel to each other? So in this case, instead of 10x plus 6y, we can say 10x plus 6y, and then instead of 0, we have 1. So what happens is if we have two lines that have the same slope, like in this case, what would happen is they never intersect each other. So we would never actually get a solution that would make sense here. So that's the whole reason why a system equation should only give us one value. Or at least as long as the other conditions aren't true, right? As long as the slopes are different to each other. Because once the slopes are same, obviously we have the scenario in which we can either get 0 or infinite many solutions. So looking at this, we have 5x plus 3y equals 0 and 2x plus y equals 5. So we can graph it, but let's say that we don't want to graph it because that would require some level of accuracy. We want to actually use some method to eliminate information. So we can use either elimination or substitution because the goal would be, okay, we're going to use the information from both equations to single out whatever point that we're looking for. For now, we're going to use the elimination method just to make it a little easier. So we have 5x plus 3y is equal to 0. We want to find some way to eliminate one of these. In this case, I think 3y might be a bit easier, so I'm going to multiply 3 on both sides. And because this is subtraction, this whole thing is negative, so this would be negative x. These cancel out, and it would be equal to negative 15. So in other words, x is equal to 15. And then I can just plug this back in and then find whichever one works. So if I say 2 times 15 plus y is equal to 5, that would just be 30 plus y is equal to 5, so y is equal to negative 25. So in other words, my solution would be 15, negative 25. Okay, so let's actually go back to this point, or this equation, and we can kind of figure out kind of how this would actually make sense. So we need to limit information here. In other words, we want to, and the reason why we're able to solve this is that for two variables, we have two equations, and neither of the equations didn't give me the same information. As I said with, what if we doubled 5x plus 3y? So the goal here is, okay, the following system of linear equations has infinitely many solutions. Okay, so let's think about what infinitely many solutions would mean in a 3D context. So the difference between this and then a normal point and a line is that we went from just a dot to actually having a line that goes through it. But if we think about 2D to 3D, that means the line would need to now be like a plane. So I can kind of show you what this will look like graphically. Okay. So looking at this, we can say, for example, x plus y plus z equals 0. And if we look here, what this means is it's kind of like a plane. So what I mean by this is if I choose an x and I choose a y, then I can choose a z as well. So this, just like before with the line, there's certain limitations even if we say we have infinite values that are involved with this. And in this case, we can kind of almost see like a 2D shape or like a plane that exists when we do this. Now what happens when we have two planes? So in this case, I'll just say x minus y plus z is equal to 0. We still get infinite solutions, because even though these planes intersect each other, if you look, it creates this line basically, right? This line is shared that can go on infinite both ways. So that means we still have infinite choices involved with these two planes. So in other words, we still have infinite solutions if we have two equations, but three variables. But what if we have three variables, or three equations? Well, now we have we're almost defining two lines. So the line between the blue and the red plane, and the line between, let's say, the green and the red plane. We can also choose the other planes if we want to, but in our case, let's just choose the green and red plane. So we can view this equation and this equation. And what happens is we only have one shared point, which adds 0, 0, 0. I can even mark it down here to make it a bit more clean. And then we see the point there. And that's the only point that's shared between all three of these planes, which would cause it to be like this. Now, let's think about the situation of how we could potentially get infinite solutions even though we have three planes. The first way we could think of this is, what if we have two planes? Let's start with just two planes. So we have two planes. What would happen for me to get another, just to keep this line essentially? Because that's the only thing that could still be the same if I were to add something new. Well, what if the plane I added was the same as one of these, right? So what if I said 2x plus 2y plus 2z is equal to 0? Well, we notice that this plane is the exact same as the first one, right? That's why it overlaps it. this would cause me to obviously get the same line, right? But there's actually another scenario that's actually interesting within 3D lines or 3D graphs that isn't the same when we normally talk about 2D graphs. What if instead we have this line and we found some plane that's still parallel to it? So what I mean by this is, what if we found some green plane that just ran through, let's say, z in this case. So I said z equals 0, or what would it be? Um, x equals 0, which is extend to 3D, or would it be y? Okay, so it would be y. So if we look, this y plane actually cuts through exactly this point, or this line. So in other words, we actually gain no new information as far as what could potentially limit us to a single point. So that's kind of what we want to deal with this problem, is how do we get no new information when given this? Because if we think about what I just did with y equals 0, let's say I put y equals 0 for both of these. So x plus z is equal to 0, x plus z is equal to 0. What happens? We just get the exact same line equation. We have the two same equations between the two of these, so we have nothing limiting that information. So going back to that, the system of equations in the previous problem, we basically had to tell ourselves, well, let's think about the first condition. What if one of the planes are the same as each other? Well, we can already tell that there's none of these that have the same proportions. There's no way for me to set k or l to a proportion such that I just get the same line. So there's no way for me to limit myself in that way so that I can get infinite solutions. Now the next way is, as I said, what if we found some way that this plane just is parallel to the line that's made by the first two? In other words, we gain no new information. So let me actually make this arrow a bit bigger. So let's come all the way down. So we have 5x plus 3y minus z is equal to 0. 2x plus y plus 3z is equal to L, and x plus 4y plus kz is equal to 10. Okay, so kind of the method we can use here is to get same information. What if I just simply said that some proportion of A, or of the first equation, plus some proportion of the second equation just gets me the third equation? Because if this is true, then this line shouldn't give me any new information. Now, this needs to be set up in two equations. We have this first equation, and the second one be 0 plus L is equal to 10, right? Or A times 0 and B times L, because we're also proportioning it to each other. So if we were to solve for the first one, which is much easier, it's just BL is equal to 10. In other words, we can also just say L is equal to 10 over B. Now on the other hand, we can distribute the A into B. So we have 5AX plus 3AY plus AZ plus 2BX plus BY plus 3BZ is equal to X plus 4Y plus KZ. In other words, I can now separate this thinking, okay, the constant here is a 1. It's the same as saying 5a plus 2b is equal to 1, because they both all share the same variable. So that's for the first one. The second one I can say 3a plus b. Let me just check here. Yep. Plus b is equal to 4. And then for the last one, I can say negative a plus 3b is equal to k. Well, just think about the case I said with two variables and two equations. We already know we can solve for a and b. So in this case, I can just double 3a, for example, here. And then we get -7 and then -a. So in other words, we have a is equal to 7. So we can now solve for b, which is, let's see, we can just put it in here. So we get 21 plus b equals 4. So b is just the same as -17. Okay, well, actually we just immediately solve for L. L is just -10/17. So that's our first one. Our second part is finding what k is. We can just simply sub a and b into here. So we have -7 plus 3 times -17 is equal to k. So if we do that, it's simply -7 plus -51 equal to k. So k is equal to -58. Okay, so that would solve this problem. We know what L and K are in order to get these infinite many solutions. And just as a sanity check, we can just simply graph this to see if we only get a line. So we get infinite many solutions. So let's plug these equations in. The first one is 5x plus 3y minus z is equal to 0. The next one is 2x plus y plus 3z is equal to -10/17. And then the last one is x plus 4y plus, or we can say -58z is equal to 10. And if we look here, we can see that the first two create this line, and then the third plane is actually completely parallel. It lines up with the line that's created by these other two planes. In other words, we're getting only a line. And that line, there's no way to constrain it. So we have no way to actually define a point. We just have infinite values that are possible within this pattern. That's all there is for this equation, really. And I think that this is a very good exercise in trying to understand what it really means when we deal with system equations, and how can we start with smaller problems that start with a more basic concept that we're more familiar with it, and we try to go up to something a bit more difficult. As always, if you have any questions, feel free to leave any comments down below, or if you feel like there's something wrong or you want a more in-depth explanation, you can always reach out to me at ben@chicagobright.com. Thank you.